unless you have some questions. Good. So what is Eclipse actually? Eclipse is an interesting thing. That the Eclipse is a technology platform developed under the open source as an open source project, where the community initiated by or launched by the IBM in November 2001. And the most vital part of the platform itself is the community, with a lot of companies working. Some of them for their own account, but some of them sharing their some elements of the Eclipse to the community with another part of the community, helping us to achieve a pretty nice product. So maybe not the best in all the categories, but a pretty nice product. In case of this Eclipse, 4 levels of membership in the Eclipse Foundations there are formally. So we have the strategic members, which contribute developers, and the resources, add-in providers, where the elements of this environment are made by them and added to the releases. Associate members, which are usually the universities and standardization bodies that want to participate in the Eclipse and development, and the members of the committee being core developers. So these are the major elements. In case of strategic developers, strategic members, couple of large companies like IBM or Borland or CA or Intel here. In case of the consumers of the Eclipse, but still strategic members, again, SAP, for example, from the large companies. Yeah, many smaller members working on the environment, with the environment, using the environment in their products. Yeah, from a perspective of microcontrollers, yeah, for example, Texas Instruments that switched their Composer Code Studio, so their IDE, to Eclipse already some time ago. And now, thanks to this, the environment got much more modern. So at least more modern look and modern operation than it used to be before the jumping on the wagon with Eclipse. The architecture of Eclipse in general is that we've got the workbench, and then we've got workspace as well, that we change. We've got the help system. We've got various components, team components, plus a lot of plugins, a lot of plugins configured easily that by some companies that are delivering us the software. All then when we get already the development environment, they are configured. They can be configured, changed during the customization process. So the system is very customizable. So you can change almost everything, adding, modifying the environment and adapting them to your need. As I mentioned, the Eclipse is a base for ADT, Android Development Toolkit, where you write in Java and use some graphical elements, and as well we use it in STM as a base for Atomic or Cube IDE, where you write in C and also have some graphical overlay. I mean about Cube here, where you can make some configurations of pre-configurations or initial configurations of the processor. So that's definitely the advantage of the Eclipse architecture, that the architecture is pretty much, or very highly, not pretty much, but very highly configurable. The Eclipse, so if you get accustomed to the Eclipse environment, because it's there is a certain learning curve, so it's not negligible. So you work with Can you hear me? Because it's unstable. I got an information about the unstable internet connection. Can you hear me? Hello, hello? Can anybody hear me?
Yeah, I can hear you.
Okay, good. I guess I got a notification about unstable connection. Anyway, Eclipse is good. And that's definitely the advantage that after this initial learning curve that we have to change when changing the environment, programming environment, Eclipse-based environments, even for different language. So jumping from Java, so ADT to STM32 is really simple because all the elements are there. So the idea about the workbench, workspace, perspectives, the plugins, so all this is the same graphically as well. The new updates are coming, are appearing, maybe not very often, but that's actually good. So at least for me, I hate monthly updates, to be honest, but they still appear pretty often, and they keep the environment up to date as well. Very important thing is that because there is such a huge environment, so there are so many companies and people using it, and there are so many various developers working on some various plugins. It means that the list of plugins is very long. You can prepare your own plugin if you want, but there is a list of interesting plugins which you can install. You can switch it on, you can switch them off. Various kinds of plugins for various kinds of sometimes universal plugins, cross-platform, I would say. Sometimes the plugins for particular platforms, that hardware platforms that you are using it for. For the software vendors itself, so the ISVs, is that they don't need to focus with the Eclipse environment, so don't need to focus anymore on the graphical layout. Maybe not completely. They can't completely neglect the graphical layout. Still, they have to. They can focus more on what's important. So on the features, on the plugins, dedicated to their particular environment. So like with the cube, they can focus on the cube graphical part, on the cube MX. They can focus on the ST itself. Can focus on the CMC core on this hardware abstraction layer, maybe, but it doesn't have to be the editor itself, or the layout of the debugger, or the configuration of the whole environment. So all this is common. And yeah, it's automatically available in the Eclipse environment. Then, of course, in case of the software vendors, they fits into an established and rapidly growing platform. So it means that it's easier as well to find people on the market that are developers in this environment. If you have your own environments, you have to keep the team, especially the core members of the environment. When you're in a company, when you are a company, you have to keep the team, because they are difficult to be replaced. Again, especially the core members. In case of the Eclipse itself, so the number of core members of important people, important software developers, is much more reduced because it's a common environment. So if there is the group of people knowing the problems with the Eclipse development, Eclipse-based environments is larger, so the prices can be lower for the people, for the workforce. And they can combine their work with other Eclipse plugins to create custom solutions. And that's actually what's happening. So it's configuration is here the king. Proper configuration is the king here. The concepts of Eclipse. So the elements that we have in Eclipse. So we have a workspace. We have a workbench. So the space where we work. A workbench is the table that we can see, the table with various elements. We have various perspectives. We have views. We have editor and preferences. So yeah, step by step, I think it's for those of you that's it's about terminology again, about having everybody on the same level, because for those of you that work on Eclipse environment, it's gonna be a bit trivial. So what is a workspace? Workspace is a physical location on the machine containing files, folders, a project itself, projects, because in one workspace we can have multiple projects and containing, of course, multiple files. So the workspace, the idea about the workspace is pretty nice. Pretty nice because you can switch if you are making different projects and projects on different platforms even, then you don't need to mix them up. You don't need to reopen the projects, close them, open them again, and have a mess on your workbench. But you can just change the workspace. You can switch the workspace and then everything changes. And then you can reconfigure it and then see different on your workbench. You can see different projects dedicated to the particular platform or particular project itself, physical one. So it's especially useful today when we work. So when we have even STM32, so when you're using the same Atomic or STM CubeIDE environment, and but we are working on different processors. So today, sometimes we have one device and 3, 4, 5 different CPUs, different CPUs there. So we need to write different softwares, different firmwares for each of the CPU. So then this is excellent. Workspace is generally just a directory. That's what generally is, but of course it's from the file point of view. From the point of view of the use of using it, it's much more, because the workspace delivers us, so switches allows us to keep an order when we work on more than one task at a time, which is again very often the case today. The workbench, this is just what you see. So the workbench itself is an environment containing the perspectives, containing views, containing editors. So all you can see on the screen is a workbench, and that's as with the programming. So I think single screen, especially if it is 15-inch or lower, it's difficult to handle usually. All the elements that are available in Eclipse, and there are really plenty of, especially if you start debugging, then quite often a good idea is to connect the larger monitor or monitors to our PC computer to see the workbench in full, to see all the elements of the workbench. And then next thing is a perspective. Perspective is formally a set of views organized for a particular task. So here, depending on we can define our own perspectives, or we can have we can use the predefined perspective. So they are, when we have the Eclipse itself, then maybe I will show you. Let me see if I have it. Oh, you can see, yeah, one of the project, and here is all this is workbench. So naturally, this is workbench in some workspace. So there is a workspace. In this workspace, as you can see, there are 3 projects at this moment. So this Project Explorer. So formally, the whole is a project. There's a view of Project Explorer, because this is a view. And the combination of the views and the editor, this is the editor, of course. The combination of views and editor gives us the so-called perspective. Yet the perspectives can be changed. So usually the perspective switch is somewhere here. If I press it after some time, the perspective would change. On the debugging, I'm using this kind of perspective. Yeah, it's not connected. That's why it's not changing anything, because normally when the debugger is connected physically, there will appear some values. Like, yeah, although, for example, this appeared. So some elements, some views in the perspective appears. Of course, all this is configurable. And here in this particular example, it's not connected. That's why all the views, like the debugger view or this view, they are empty because I did configure them. So, but you can configure. Normally, you can configure the views to your needs. Actually, to your needs, everything is configured here with the perspective, which you can customize. Of course, you can open particular perspective. You can modify the perspective in a certain way, and then in the particular perspective, you can choose which view you want to see. So again, it depends what you are doing. It depends what's your intention. Of course, it depends what platform you're using, because this is the example on STM32 platform. Again, Eclipse is very universal, so it can be used in various for various operations. But that's the difference. So that's about the perspective, about the view, what's the difference, and the editor. So formally, getting back, perspective, set of views organized for a particular task, and perspective lets arranging the view to the needs. Normally, there are several perspectives installed. As I try to show you, it depends on the Eclipse which you're using. There can be different. Yeah, here on this example, you can see some examples of the perspectives that can be available, but still you can build your own perspective and your own set of views. Customization of perspective. So we have the menu, changing the perspective, customizing, saving it. So adding some comments, some elements. Everything is really customizable. In case of a view formally is a window on some resources in the workspace. The views can be open, close, arranged in any way necessary, and the views again can be switched on, switch off during the perspective configuration, but also during normal operation. You can hide views, you can open the views, you can add new views, you can remove the views from the perspective, and then you can save the perspective as a new thing, or it will be automatically saved when you leave the project and when the workbench is closed. Then the current set of views on the currently modified perspective would be stored, so that you can reopen it automatically. It will be then reopened automatically when you restart the workbench. Yeah, naturally, two views may display the same thing in different ways. For example, registers, in case of microcontrollers, for example, memory dump, for example, variables. So various debugging information. They can be sometimes there are different options allowing us for displaying different data. The information in a different way, better for us for particular application. Yeah, some examples of the views of the same. So package explorer and navigator. So you can see the file structure, the project structure on the example of Android development toolkit here, to have some different perspective, and not only the perspective of STM32. Showing us the functions on the left with package explorer, with the elements, modules, procedures, whatever is whichever language are we using, and the right where just the files are visible. Different views are possible. Yeah, and then we get to the preferences, which are really abundant. So we choose window preferences, and then we go to the preferences dialog. And as I wrote down in the last line, just about everything can be changed. There are sometimes too many preferences, so that's honestly, for a beginner, that's a problem. It's one of the reasons that during laboratory we decided you should use Kyle instead of the free of charge STM32 Cube ID, because Kyle is a licensed software, while the Cube is for free. But the Kyle is simpler. The Kyle configuration, although still there are a lot of options that you can choose, but it's easier. It's easier to handle it, to grasp it in the beginning. In case of Eclipse, the number of options is overwhelming. To be honest, in the beginning at least, it's overwhelming because you can configure not only the graphical layout, the graphical view, all the elements of the graphics of the workbench, but also, of course, you can configure the elements concerning your project, concerning your platform, from the choice of the compiler through the options of the linker, assembler, linker, optimization, debugging. So all this and many more. So to the elements, to the behavior of the editor, the editor itself, and editors itself, and the choice of the views. So all this can be modified, and as well we can add some plugins here, and then with different plugins we will have some new options available, which means that we can really customize the Eclipse. We can personalize, not even customize, but I would even say that we can pretty easily personalize the Eclipse to our needs. Yeah, so many preferences here. Some of the preferences are dedicated to this particular example. And of course, the number of preferences changes with the plugins installed. So the plugins, some plugins are adding the preferences to the list, and then you can modify the plugins themselves with the use of the preferences. Yeah, in case of IDE functions, even with the standard set, a standard optionality, we've got quite a lot of features. Of course, we can search globally, locally, various methods of searching. We can make bookmarking. We can put some tasks that are to be done, that are still missing. We have a local history. We can make a file comparison. We can, of course, import, export everything. We have support for team functions, although they are not included in the standard Eclipse, but you can add easily a server for team functions. And of course, various file manipulation, so navigation, cut, copy, paste. So it's really abundance of functions from all those categories and even more. So the IDE is really complete. So almost anything you would like to have in programming environment is there. If not, then then you can find it, you can modify it, you can upgrade it through the existing plugins. Yeah, so the search, it's theoretically search is a search, but it works better. It simply works better. So it's really sometimes the Eclipse environment, it's very difficult from the start. So when you enter this world, so it seems pretty difficult. But when you get accustomed to it, then you start to find other development environment ancient and unpleasant to use, to be honest, especially from this simple elements point of view. So the editor itself, so the compilation, it's more or less the same. So sometimes, for example, in Kyle, it's easier to configure the memories, it's easier to configure the various attributes and pragmas and so on. But the Eclipse wins with the standard functionality. So all the such simple things like the stupid search. Yeah, compare Atmel Studio Search, how abysmal it is, how abysmally bad it is, I would say, because it's really a simple, but when you are making a project concerning 40, 50, 100 different files, a good search engine is really required. And it's there. So in Eclipse, it's really there. It's not so obvious for other softwares. It's always Control F working, but sometimes it's really lousy. And in case of Eclipse, it's working and it's even customizable for various kinds of search. So you can change. You can decide. So here is an example of the view the window that opens when you want to search. But take a look at the files. So even here, it files a Java search, plugin search, which means that you can search for methods, constructors, packages, fields. So plenty of options we have, and the options as well depend on the plugins that we have installed. So we can really we can really obtain here a very complex search engine. That's excellent. That's really excellent. Next thing, bookmarking and tasking, which is placing a bookmark first. So the bookmark first is the area where, so we put it on the side, this, because by bookmark I mean of course this kind of thing, and then we see on the right side of the project this bookmark, because it's on the left when we are in the range on the editor, and then on the scrolling it's usually a blue rectangle on the right side of the project. Then we can very easily jump between various projects, within the bookmark, but using bookmarks within the project between the files, because we can have bookmarks listed, so we can open the view showing us the bookmarks, and then when double clicking on the bookmark, we can jump from file to file. From file to file, we can jump very easily, and then make some modifications or change or check something or use it during debugging. So various options we can have with the bookmarking. A task is pretty similar, in fact, to the bookmark. Yet formally it's a bit different thing, because formally the description of the task is important. The idea is the same, so that we mark the thing that needs to be done. It has a different symbol. It is a task, not a bookmark. But with a task, we usually make some description of our remarks. So instead of putting a comment, because we can always place here at this place a comment and use a bookmark. It will work the same. Functionally, it would be the same. But with the task, we can just simply write a note in a task and build a to-do list. Your own to-do list, you can build that. So again, similar thing, small thing, but yeah, working. Next important thing is the local history. It's a local history which is there, which means that you can it's really a mini version of VCS, a mini version control system. So you don't have versions, but you have snapshots available of how you are modifying the files project during the day, and you can easily jump back to various modifications. So it's if you know, I think you know. I hope that you're that experienced and you have already met it in practice, so that it's pretty important, this functionality, so that you can rewind back. Sometimes we go too far, sometimes our ideas are not working, and sometimes it's really better to go back and take it from the point we were 2 hours ago. So of course we could use a version control system, full version control system, or we can start playing with committing on something like GitHub. But it's more time consuming usually. So it's for smaller changes. This local history is naturally for something smaller. So it's something that we are modifying one procedure. We're not changing the whole code. And then we would just want to jump back or get rid of our changes that were dated just within a day, not within a week or months, like we do with committing something. Then to GitHub. Then there is a function of comparing files. Very basic function, again, basic but important from practical point of view. So these are the small details that matter, so that we can have the comparison. We don't need another software. We can make the comparison directly inside. the program. And as well, we can export import. So this is pretty normal. So nothing really special, and many other features. So, there are trivial things like going somewhere, so jumping when we don't use a bookmark. So then when we don't use bookmarking, then instead of this, we can use go to. So then we can jump to a file, you can jump to a line, we can jump to some tape or package. It also works. So this is this direct going somewhere is also pretty nice if we will do use of a control and using a mouse button. So take a look how it works. So if you want to get to references, so now I'm pressing left control, and then when I click with left mouse button, I go to the reference. So then I don't need to use a go to. So it's much simpler. And again, navigating through code when having larger projects is pretty important, because we have various things in various files. Even if the files are well described, and there are a lot of comments then navigating, so jumping back and forth. So that's why tasks, bookmarks, and this kind of go-to functionality, again, small thing, but in my opinion, very important from practical point of view. Copying, that's maybe not very important. Team functions, so that there is a support, again, something that we expect from every environment today, because the projects are getting very complicated sometimes, and there are teams working on this project that's even in microcontrollers today. And what is even more, there are teams working around the clock, around the globe, which means that the version control system and the team in general, the team functions, they are pretty critical. They've been pretty critical recently, and they will be in the future to come. So we need just some plugin for this, but still there is the support, so we can have we can install it pretty easily and use either free of charge control system or some more complex. All this is possible. In case of debugging, that's the view that can be seen. That's the perspective, debug perspective. Actually, in this example about Java, in case of Cube or Atomic, the perspective is a bit different. In case of Code Composer Studio of Texas Instruments, is another idea about the perspectives. Still, if you don't like the standard view of perspective, a standard set of views in a particular perspective, this kind of debug perspective, then you just get rid of it and reconfigure everything. That's I think quite natural and quite straightforward. So summing up or concluding, the Eclipse platform, the Eclipse software platform, is not the only one on the market. There are many. There's a competition, in fact, a bit. Yet the Eclipse is vital today, as it defines the graphical user interface and the experience of the developer very much. And because of this customizability, it can be really adapted to the particular developer need. And when you are a developer, then you have your own wishes about everything, and that's excellent. That's splendid with the Eclipse, that you can really get it. So you don't need to just put it on a wish list that maybe someday somebody will do it, but you can really and deliver to you. But you can really do it on your own, just by modifying the perspectives and or installing new plugins, new views. Good. That's it about the Eclipse. And according to the plan, we are changing the subject towards on-chip debugging. In case of debugging, historically speaking, or viewing it from historical point of view, in the beginning, there was no access to the microcontrollers. So in the beginning, so I don't know if you still remember last semester and a lecture about 8051, but those times the architecture was that there was a microcontroller, so actually 8051 with on-chip RAM, or 8052 with on-chip ROM. In general, PROM. There was inside PROM, which means that the PROM was used by large factories. Normal users for small and medium size had no access to it. And the program was connected in external EEPROM, usually memory, which was connected through the extension bus, so address and data bus. No programming, no access to the core available. The program itself, no need to reprogram it because the program was hidden in the EEPROM. So changing the program, changing the machine code required changing the content of the EEPROM. There was usually EEPROM. Later there came flash memory, but in 80s it was mostly EEPROM. Naturally, this was not interesting. The difficulty was here with the necessity to connect many lines, some glue logic plus the EEPROM itself. So everything was large, everything was expensive, everything was error prone. That's why in later processors, like for example, in the AVRs, various AVR units, we have the AVR itself, the core, but the memory already, the flash memory was integrated inside. Which means that we needed a method to get and change the flash, comparing to the classical EEPROM. And two methods were delivered here for getting into the flash. First method, so-called in-system programmable method, in-system programmability method, was the method where some internal application took over control about the programming, and the in-system programming method is the method where usually the JTAG, so-called JTAG interface was used. A bit later on, a new method called in-app programming appeared, where the difference about the in-system programming and in-app programming is that for in-app programming there is used a standard interface like today USB, UART, SPI, I2C some. I saw the I2C, but parallel interface, it was used for this purpose as well. In this in-app programming, the difference was that first, so we needed to upload all the programming algorithm first to the core itself, then the core itself started communication through this dedicated interface. Starts because this method is used today, and starts the data exchange, data uploading to the flash, modifying the flash from PC applications. So two methods appeared on the market, so in-system programming and in-app programming. The method with in-system programming, the difference is that by ISP method, I understand the interfaces and the methods which have access to dedicated peripherals, while in-app programming are using the standard peripherals available in the microcontroller. As the difference, in case of ISP, the major interface that is responsible for ISP programming is the JTAG today, the most universal interface. We'll talk about it after a break. The second one that is customized to Cortex microcontrollers, it's a simplified JTAG known under the name of SWD. So the difference between those interfaces already after a break. So let's have 15 minutes break and we'll be back after this. Okay, welcome back. Welcome back after a short break. So we move back to the on-chip debugging. In case of in-app programming, we'll not get there, as this is dedicated to the, as I tried to mention in the beginning, it's dedicated to the, it's different between devices. Rather, we'll focus on the JTAG and SWD interfaces, and they are a bit more universal. So JTAG is generally universal because you can use it in industry in various applications, about controlling electronic and programming and debugging and monitoring the electronic devices. SWD is Cortex dedicated still because of the importance of Cortex. It's important as well for us. So we'll focus on the on-chip debugging. Generally, why we need the debugging anyway. So first of all, we want to check. So a couple of things we want to check. Pretty obvious, I think. So first thing, the debugging tracing of the program tells us where the program has been and how it got there and for how long. Especially interesting is this how it got there, because or in general, those three informations are not that obvious outside, requiring sometimes some skill to get it. But yeah, that's actually why we need the debugging tracing. Nasty problems can often be found quickly with tracing. That's definitely true. That's definitely true. Of course, if nasty problems can be found, then simple problems can be found simpler. Without the use of on-chip debugging, it really an oscilloscope is necessary, and even then, debugging takes a few times longer, at least, than with the on-chip debugging. Yeah, especially where the bugs can be found quickly, especially where the bugs occur a long time before the consequences can be seen. Next thing about the tracing is that we have some kind of a history, so we can monitor everything, and we can display everything in the screen, forming of a PC, forming kind of a history, and then we can, with the analysis of the history, we can then get the information. All this is possible only with the proper debugging and tracing available. As well, we can check the race conditions. We can find the race conditions. Really big benefit here. That's true. So if there are two things happening at the same time in a microcontroller, and for example, in one clock cycle, something is switching something on, and in the next clock cycle, something else is switching this flag or semaphore off. That normally it's very, very difficult to find this kind of thing. With the debugging tracing, yeah, not maybe extremely simple, but possible. Another problem why the debugging and tracing is so vital, so important, is the use of operating system, where many things are happening at the same time, and then stopping the code, stopping of a microcontroller operating system, and even worse, it is with multiple core. So the debugging of multiple cores without on-chip debugging, without the tracing capabilities, possible, of course, but not really. What kind of problems we can find with tracing? Plenty of problems. Yet the most nasty, the worst ones, and the ones that are causing the largest damage. So first thing, pointer problems. Very common, very common thing in the microcontroller. So first thing that we go, in case of pointer, from a couple of perspectives. First perspective that we have, in first example, and first category of this pointer problems, we have the microcontroller, and we have some kind of table array. We define space for the array for, so 20 cells, something like this. And then we start using the array, and then the array, we write we use an index 20 then. That's a very common mistake. While in C, the indexes are addressed 0 to 19, it should be addressed from 0 to 19 and not 20, which means that we get over the table, and this is a pointer problem. And we modify something that's, that may be important, but maybe not important, but maybe critically important. Another problem from this category that debugging tracing helps us to find out is that we want to read from the memory that is not existing, or we want to write to a memory location which is not existing or which is improper. So non-existing is simpler to tackle, because on our microcontrollers, for example, if you want to write something to a non-existing area in a memory, you get a hard fault. So there's an interrupt. It's automatic. So you get a hard fault, and in the hard fault, you have an information something work happened. But in the smaller microcontrollers, and when you are just trying to access with wrong pointer a wrong place in an existing memory, you don't get this kind of error. You don't have this problem. And this is a serious issue. This is usually a very serious issue. So the pointer problems. This is from my experience, it's the most common problem. In fact, the most common category of the problems from these difficult problems, from not some trivial syntax problems, syntax issues, also misunderstandings of the functionality of peripherals. But from the practical physical errors, this is the worst category, pointer problems. And with the debugging, we can easily see where the problem is. Easily. It's not that it's automatic, so sometimes we need to search a bit, but controlling the registers and observing the pointers, monitoring the pointer itself, we can see that it was used in an illegal way, in the wrong way, and then that we got off the table as well. We can see this and what modifications we did. So that's something that's very nasty and very problematic normally, and with debugging tracing, we can pinpoint it and eliminate this kind of bug. Next thing, illegal instructions and data aborts. For example, misaligned writes. When we talk about microcontrollers, especially any kind of microcontrollers, they have certain alignment of writing words. Bytes, it's not a problem, because byte is always single byte aligned, so it's always written properly. But when we have when we want to write a double word, for example, and it can be shifted by 1 byte, 2 bytes, or 3 bytes from the location, so it's not well aligned. It's about reading and writing, so it means that you can get wrong. Either you write wrong value or you can read wrong value, because it's actually you read a few bytes proper and a few bytes wrong, in the wrong way, from wrong data. Or even wrong instruction, because if we talk about misaligned reads, then we can talk about misaligned reads from the instruction memory as well. So in unified memory space, it can happen. It is possible. And again, with debugger, that's possible. So you can pinpoint it. You can find out what the problem is. Without debugger, finding this takes ages. Next thing, code overrides. For example, writes to flash, unexpected writes to special function registers, or various kinds of registers, as well corrupted stack. So that the stack starts to overlap with, because the stack is growing up, while the data, the variables, various kinds, are growing down. It should not be a problem. So theoretically, so it's not a problem with the variables themselves, because even if you use a malloc function or allocation function, but by the way, because I don't know if we talked about it, what's the difference in microcontrollers between stack and heap? Because I don't remember if we were explaining this. What's the difference between stack and heap? Who knows? Who remembers? Just to wake you up. What's the difference between those two things? Usually we have them both configured in an environment, but what's the difference? Stack and heap. Anybody? In Polish, heap is sterta. Stos is sterta. That's in Polish. Stack and heap. What's the difference? I have a chat response.
So on the heap, we store global variables, and in stack, we store temporary and the ones which were assigned during the execution of code. Speaking of variables, of course, the difference would be.
Almost. Jakub also responded the stack is managed by compiler, heap by the programmer. No, that's not true. Both of them are managed by stack is managed in hardware. So I would put this way: stack is managed in hardware, heap is managed by the compiler itself, by the software. Maybe this way. What's the difference? The stack is for storing temporary variables, for storing the addresses. Generally, it's for hardware use. It's used physically, for example, for passing variables, for passing temporary variables, automatic variables, for storing temporary automatic variables when you have C procedure, and as well for passing arguments between the functions. So if you have many arguments which are passed by value, then the values are usually stored in stack. So if there's enough registers, then the compiler uses registers. If not, they are stored on stack, passed through stack to the function procedure interrupt service routine. Heap is only for variables which are allocated dynamically. So stack is for static variables, for static kept variables. Static, not static, because in C static is something different. But stack is for variables that are known during the compilation. It's automatic because it's so it changes, its size changes because we can have different nesting, and with each nesting it's used not only for the variables but also for storing registers, for stacking the registers and program counter. Heap is something completely different. It's a software structure, so the idea is the same, so that we have first in first out, last in first out structure, because both of them are LIFO structures. But in case of heap, this is used from software point of view. This is used by the compiler when we allocate the memory. So when you use new, for example, in C++, or you use malloc, calloc, then you will get the memory from the heap, not from all of the memory. You will just get the memory from the heap. That's why we set the heap. It's in the project. So if you open the project, any project on STM32, you will see that the stack and heap, the stack size and heap size are defined. The stack, this definition, that's a bit tricky because the heap, the size definition of heap is used, in fact. So you will not be able to obtain from new or malloc or calloc, you won't be able to obtain more memory than it's dedicated to the heap. So normally the heap has like a kilobyte or something like this, which you can free if you don't need it, if you want use memory allocation functions. So you can free it, or if you intend using dynamic allocation, memory allocation in your code, you must increase the heap size. In the compiler, it's in the various options in Kylist. It is compiled in the preferences. It is visible in preferences in CubeID. It's in the assembly file, in the startup file. The stack on the other side, although there is also usually a dedicated size of the stack, but it's not controlled. So here we have to be careful. So initially the compiler, if you choose it, that it will be 500 bytes or 1 kilobyte. So initially the compiler books a memory so that there is a space for 500 or 1 kilobyte of stack. so of free memory, so that no variable will be put there. But then if you start making too much nesting, so or if you start using the stack too extensively about passing the variables, about making operations on stack, because it's also quite popular to work on stack with calculations, to treat it as a temporary variable, then you can overflow the stack. And then, of course, and then with the stack can grow beyond its dedicated size and can overflow the heap, because usually it's the heap above. But sometimes it can even go that far as to start eating up, let's say, or damaging the stack itself, can start damaging the normal variables, global static variables that we have in our code. Also, there may be a problem with corrupted stack, so that in the area where the stack is, accidentally, because of the pointer problem, we can actually write something. So this is very much connected to the pointer problem. Again, something that we can trace with the debugger, and the debugger is the best tool to do this. This kind of problems may, of course, happen. We want to avoid it. And next thing, out of bounds data. Naturally, again, simple thing, very easily, that can be very easily seen on the debugger and tracer. So the use of a variable which is non-initialized. We have a warning about it, that if we want to use a variable which is non-initialized. So the compiler gives us a warning, but yeah, not always we read warnings. Sometimes we just care about the errors, and we are very happy that our project did compile, so we don't read, so we neglect it. And that's, of course, a problem. We shouldn't be this way, but happens. So in case of debugger tracer, when we use it, we can pinpoint this kind of a problem very easily, because we just pause, breakpoint the code, and observe the value of a register, of a peripheral register of a variable, and then we can very easily see, okay, that's the problem. So the data should be 0 or 1, and it's like 1 million or some trash. Next thing, more difficult, I think, to trace is finding the programs, the part of our code which are occupying too much, which are eating up too much clock cycles of the CPU. Such a possibility exists, not in all microcontrollers, but it exists, and it's an important thing, especially when we talk about the operating systems and the tasks and applications that are there in the operating systems. If the operating system is switching the tasks, so if we have a preemptive multitasking, and usually we don't care that much, but if our software structure is more about cooperative multitasking, it doesn't have to be even the operating system included. You can even write by yourself the cooperative multitasking. So write the round robin with interrupts, for example, with this structure. Then pinpointing slow programs becomes important, because a slower procedure, slower process, slower task, of course, slows down the whole control loop, which may have repercussions, various kinds of repercussions in the real life. In case of debugging and tracing, again, we don't need to use an oscilloscope. Normally, we use just an oscilloscope and observe the scope, the pulse, some LED blinking or some pin changing, and counting the time. So that's what we use without the debugging tracing. Yet with debugging tracing, we can try to pinpoint the problem easily by observing the clock, for example. If not even special tools no special tools have to be used, because it's enough really to make a breakpoint and step execution, and then just to check the time of the processor to see what's the problem. Yeah, naturally, Stack Overflow, we talked about it before. Runaway programs, that's very much connected with illegal instructions. So the illegal instructions, yeah, what is runaway program? The program that's it got a legal instruction, usually misaligned. That's usually the case, so that we have a false pointer and or we have a misaligned. So again, if there is a misalignment, it's usually about because of the false pointer problems. That's why the mother of all the problems is usually the top one, the first problem here on this list. But runaway programs mean that they start to understand the machine code in a different way. It's possible. This misaligned reading of instructions starts to give us illegal instructions, but not all of the combinations will be illegal. That's a bit funny. And program may be working. And yeah, I remember such situations that with the program was working, and yeah, from time to time an illegal instruction, but most of the instructions were doing something because the combination of bytes misaligned. Okay, from practical point of view, such a program, runaway program, has absolutely no sense because it makes nothing. Yet it makes nothing, but it may damage something. It may, of course, hang up. It may start resetting. So it may be harmful even. So it won't do anything good, but it may be harmful. And then finding out what causes the runaway, where is the problem, where is this pointer misaligned? Again, without the on-chip debugging, on-chip tracing, it becomes pretty challenging. Yeah, we can try as well to find the communication protocol and timing issues. So monitor the various peripherals as well, because it's not on the list, but here we can try to modify with the debugging tracing as well. Very important functionality of debugger and tracer. As you know, we can modify. First of all, we can modify the hardware. We can see the hardware, monitor, not modify, but monitor the hardware without the use of an oscilloscope. To some extent, it's possible, and monitor the ports. So in case of STM32, you've got GPIOs, and you can see the ports of how they are changing, what's the state of the port, and then you can observe if some sensors or some other digital electronics is delivering proper signals to your microcontroller. You can also very easily monitor here. It's not always replacing the use of oscilloscope, but still it simplifies the analysis and simplifies pinpointing the problem during the use of communication protocols, various kinds. So the SPI, UART, I2C, so simple protocols, especially the SPI, but sometimes not so simple to be traced. So I hope that you will play with SPI a bit during the project, the laboratory, so that you will have a chance to check out how sometimes difficult it is to configure this trivial protocol all in all, because SPI is one of the simplest communication protocol available on the market, and how difficult it is to configure it on different levels, so on the hardware level and then on the frame level as well, to get some information, some valid information from. There is an accelerometer on the board connected to a microcontroller. So yeah, you should. It's in the program of the course. So I hope that that my colleagues will guide you there with the SPI and configuration, and you will see how important then is that the debugger to see. Again, the oscilloscope sometimes is also very useful, but already the debugger and information from this on-chip debugging deliver us information about how is it functioning properly or not, this communication protocol, this kind of peripheral, and are we receiving the expected content or not. So formally, OCD is a method to start, stop, or read the core or use the applications by having additional silicon. Take a look, additional head silicon on every MCU of a different, distinct manufacturer series. Important thing is that we can start, stop, or read the core by having additional silicon. So it's not so it has to be some there has to be some blocks. They appeared, for example, last week when we were analyzing comparing the various ARM cores, and that's the case. To access specific this specific MCU area, one or more dedicated lines are used that are then no longer available to the user. And some microcontrollers, this dedicated area has dedicated pins. On some microcontrollers, those pins are shared with general purpose, and they are activated only in certain modes of the microcontroller. So it depends. Some microcontrollers, various cases available on the market. So it works this way or that way. Normally, those pins are not really compatible with a computer. So normally, we need to connect this type of interface. Various types of interfaces are available in the market. Yet, from our perspective, JTAG and SWD are important. Still, there has to be some device that will translate this JTAG or SWD, so this dedicated interface, into something that is known to a PC computer. So usually it's USB today. There used to be a COM port in the past, but today, as you know very well, there are no computers with COMs available anymore. Sometimes it's Ethernet, although Ethernet is expensive, and usually in simple debuggers, there is no Ethernet available, just a USB or COM port. Yeah, the interface itself, yeah, we have to simply buy it. So it's different. Usually it requires dedicated software. So we have usually the each interface has its own software that is used for communicating between the PC computer and the PC software, and the board and the processor on board. So that's this is usually how it works. Main interfaces that we can connect are in case of ARM controllers, there are 3. No, not all of them are available all the time. Sometimes we have just SWD. Sometimes we have a combination of SWD and JTAG, and sometimes we have additionally extra ETM interface. Although it's expensive and it's rather rare, still happens. Comparison of those interfaces. So the original JTAG interface, the original requires 5 pins plus ground. The original JTAG interface. ETM requires more lines because it's about 5 to 10 lines, and the SWD is the simplest and requires 2, or with SWO line with the tracing capability, it's 3 lines. So it's simpler. It's simpler and smaller. In case of the capabilities, so in case of connector, maybe this thing from this table. And then there are standardized connectors for the ETM itself, 27 pin microtor connector, so expensive. But in case of the JTAG, and SWD, there are 2 small interfaces. Nothing is there. Nothing is there available. We can have, in case of capabilities for JTAG and SWD, because we are more interested in this. There are certain differences, but maybe let's move to the we will compare them a bit later. In case of ETM, this interface is rather out of scope, so it allows more. Maybe this way, because not to get into too much details. ETM requires complex connection. ETM requires complex hardware and expensive hardware to be connected to a microcontroller. Yet the advantage of the ETM is that we can rewind back our code. So if anything happens, if our code explodes, then we have a history. We can rewind it back. With JTAG and SWD, it's not really possible. Yet JTAG and SWD, as was in the table, are much simpler. Let's focus maybe not on the ETM, which is out of range usually and impossible to be used in smaller microcontrollers, to the interfaces that we usually have. So the standard industry standard is the JTAG interface. JTAG is the interface which is even defined in a document of IEEE organization 1149.1, which and stands for Joint Test Access Group. So that's this interface, the name. It's the industry standard since 1980s for chip testing. So we can, with this interface, we can feed the instructions and test data to the component under test, and the components are connected on in a chain level, physically as a chain, which means that we can access through the single JTAG interface, we can access multiple devices on the line, and this helps us to monitor a device in a complex way, because we can see, we can modify, we can add test data, but we can also get some values, so we can monitor the registers. Of course, we can change the firmware, so this the flash content of the program, of the piece of a chip, and thanks to this, the JTAG is so universal that not only at chip level, so not only to single chip we can connect, but because of its characteristics, we can connect, we can check the whole PCB, or even we can try it on a system level where we have a connection of the chips between or boards inside a device, so that we have many boards connected, and then we can modify them, all the elements, connected elements, modify, observe, monitor all the elements that are on the particular board. With JTAG, it's possible because it's a debugging and programming, and it can be used for debugging and or for programming. So if the JTAG is implemented, then first of all we can start stop program. Second thing, we can single step source or assembly line. We can set breakpoints and watch points. So we can set the point where the program will stop, or the watch point, so what we will be observing. We can read-write memory, but only when the CPU is stopped. So when the CPU is running, we can't read the memory. And as well, we can program. We can change the content. So we can change the content of the flash memory as well. And this is the major discerning feature from the SWD. The JTAG can be connected in a chain, which means that we can connect many devices. We can connect many devices and just observe one after another, or modify, program one after another. At least 5 lines, as mentioned, we have here. So 4 lines plus ground. Usually we have 5. There are 5 lines plus ground used, but there can be 6 lines plus ground. So the lines are TMS, TCK, TDI, TDO, reset, and RTCK. The TMS, so everything is synchronous to the clock set by the master. So this is the TCK. The test clock, the TMS pin is used for setting the pin, the mode of changing the mode of the JTAG block. The TDI is the test data input, which is the data input for the shift register. Then we have TDO, which is the data output. Reset TRST is not really necessary, because this is the clock return after the the TRST, sorry, it's of course the reset, which is sometimes important, not always. Yeah, and the not important signal, which is usually omitted, is the RTCK, which is the return test clock, not used usually in practical applications. That JTAG requires special hardware interface for connecting, for translating those signals to a USB usually. Today, fortunately, the JTAG interface today is not that expensive, so we can buy it for a few tens of euros, so 20, 30 euros, and you still can get some JTAG interface, although dedicated to a particular platform, dedicated from driver's point of view, because this part is common. This part is common, so the part with the with JTAG signals, this part is common between the platforms. All the chips on the market supporting JTAG interface, they have this TCK, TMA, TMS, TDI, TDO, and sometimes TRST. Sometimes the difference between the various programmers is the supporting software on a PC computer. That's why one JTAG programmer, so JTAG programmers are not universal, but they are not universal not because of the hardware. Hardware is universal, but because of the, unfortunately, software and drivers. So yeah, you can usually they don't match. It doesn't match. So there is no universal, unfortunately, JTAG software available. No, internally, in case of JTAG, we have a connection. So there is the JTAG itself has so-called JTAG cells, and by driving the TMS, TDI, and TCK signals appropriately or in the right order, we can modify the content of JTAG cells. And for example, we can modify the pins, physical pins. So we can read the pins, but or we can modify the values on these pins. Internally inside the microcontroller, there are a couple of registers for JTAG operation. The registers where we are with the use of TMS, we can put some instructions, we can put some data, and from which we can read some data to the PC, back to the PC computer. So we've got instruction register, bypass, ID register, and some other registers, in fact, inside. From the register's point of view, so instruction register holds the current instruction register, the current instruction, basically. The data register is, there are 3 data registers, so boundary scan register, bypass, and ID code register. Also maybe other register data depending on particular application. Data, as the name suggests, consists of the data that we get. In case of JTAG, the communication, so yeah, there are plenty of details that I would not like to follow. But generally, in case of JTAG, there is a lot of a very important thing about the JTAG is that that's the state machine. No, maybe this one, the state machine, because depending on the setting of the state machine, the JTAG in a processor finds itself in a certain state. The changing of the state, jumping between states, as you can see, is a combination of TMS state and the clocking. So depending on the clocking, we go to certain states, and then either the instruction or the data register can be either uploaded or downloaded from the microcontroller. So actually, a lot of things are happening, and not that trivial as it is in SWD. So there's really quite a lot of switching with the TMS signal and then with TDI. and TDO lines. This JTAG is not really that trivial. Important thing in case of JTAG is so-called another important thing, and another characteristic thing is so-called BSDL. BSDL stands for Boundary Scan Description Language, and this is necessary. So every manufacturer must provide this BSDL file showing how the JTAG aspects. How the JTAG is working, but in general, the BSDL is for boundary scanning of the devices connected to JTAG. So we have, because we can have a chain of devices, and there is a special procedure of boundary scanning where all the devices connected to JTAG interface are recognized. The recognition is possible because exactly this boundary scan description language. So it means that if the devices understand what they are asked for or asked about, and they respond during the boundary scan procedure, that they respond with their ID, with their capabilities, and then we can as a user, then we have information what kind of device is connected and what for. BSDL finds, it consists of some components, but these are actually details, so plenty of elements telling how this works. More interestingly, connection. So JTAG, we have a chain, which means that we've got TMS and TCK starway in a busway or starway, TCK, and TDO are connected in a chain way. You're forming a chain. That's important about the JTAG, and that's also important about the boundary scanning, because in boundary scanning, the devices are returning their ID, and then when we try to communicate with the devices, then we can use the ID for setting up connections, for sending frames. So the information in general go through the chain of JTAG blocks. Through all the devices that are connected to the chain. It's very characteristic to JTAG this kind of architecture, chain architecture of the TDI and TDO. Competition to JTAG, simplification, maybe not a competition, but a simplification of JTAG is the interface SWD. The main idea about the SWD was to deliver a debugging interface that would be simpler than JTAG, and that would not require such a complex hardware. So the major issue in JTAG is actually this. It's actually this tree. So many. It's pretty complicated. This state switching, which means that the hardware interfacing between the UART or USB or whatever is there to JTAG requires a lot of processing. And SWD, the idea about SWD was to avoid it, was to make to deliver to the market something simpler, yet giving us full information about the internals of a microcontroller, the debugging capabilities, the debugging and tracing. But more already, because it's already a break, so more details concerning the SWD, how much different the architecture of SWD is different from architecture of JTAG interface, about all this already next week. Any questions? Maybe. If no, thank you very much for your attention. See you next week. Unfortunately, probably again remotely. Let's hope it will change during the semester, but we'll see. Thank you very much for your attention. Have a nice afternoon. Goodbye.
Goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Goodbye.